All right, so today we're talking similarity, specifically in the coordinate plane, but we'll also talk general similarity for just a moment. This is following our unit on congruence in the coordinate plane. So it's going to kind of combine the concepts there with translation, rotation, reflection, with our 4.5 section on dilation, which remember that wasn't considered a congruence transformation because the shapes didn't stay the same. One of them got bigger than the other or smaller, but it is considered a similarity transformation, and that's what we call similar in geometry, when a shape preserves all the same proportions, just is smaller or larger than the original. So with that, kind of looking at the specific definition of what it means for two shapes to be similar here in general, it means that corresponding angles are congruent. So the angles stay the same. It's the sides that are changing here. The corresponding sides have the same ratio or scale factor between them. All right, so looking at our example here, we've got triangle ABC and DEF. For the moment, I'm going to change that X to a 6 because today we're not going to get into that aspect of similarity of solving for missing sides and stuff. Instead, we're taking this more in a coordinate plane transformation direction. So anyhow, if triangle ABC is similar to triangle DEF, also note this is the symbol for similar. It's like the congruent symbol, but without the equal sign underneath. So if that's the case, then angle A is congruent to angle D because the letter order still matters, and those are the first two letters. And then angle B goes with angle E since that's the next letter. And then angle C is going to be congruent to angle F since that's the third letter. So that part stays the same as when we talked about congruence. The part that changes is instead of having the sides be congruent, they're going to be in a ratio together, and it's going to be the same as all the other ratios. So in this case, if we start with the first two letters, AB, I'm going to put them on top of the fraction, and then DE, the first two letters over here, are going to go on the bottom. And we can do this with letters. We can also do it, since this is a more specific example, with the actual numbers. So 15 over 6. Since AB is 15 and DE is 6. Then we'll move on to the next one, BC, the last two letters, with EF, the last two letters. All right, well then BC was 10 and EF was 4. And then lastly, our remaining side, we have AC, the first and last letter, with DF, the first and last letter there. And AC was 5 and DF was 2. So note all of the ones from the same triangle. So all of the ones from the bigger triangle are on top. All of the ones from the smaller triangle on the bottom. You could reverse it, but you would have to reverse it for all three ratios. So if all three of these fractions are the same, that means that these two triangles would be similar. And if they're similar, then all of these fractions have to be the same. You can tell by either reducing the fractions, go 15 over 6 and 10 over 4, those both reduce to 5 over 2. Or you could divide them all in a calculator and notice that this as a decimal is 2.5. Either way, this is also known as our scale factor. So we talked about scale factor with dilation. That tells me that this bigger triangle is 2.5 times bigger than the small triangle. All right, so that's kind of in general what similarity looks like. In the coordinate plane, this is more what we're going to be focusing on today. If these two things are considered similar, how can I get from one of them to the other? How can I get from x, y, z to x prime, y prime, z prime? And there's often, just like with congruence transformations, there's often more than one way to get there. And sometimes one way might be easier than another or take less steps than another, but neither of them is necessarily incorrect. They're just different. And there's certain things that you can do to make, to notice what might be easier and stuff like that. So we'll get into that too. Starting off here, I would probably want to start by figuring out what my scale factor is going to be. The easiest way to do that is to look for sides that are horizontal or vertical and count the length. For example, this side is 4 units long and this one is 8 units long. And so my scale factor is the side from the new shape divided by the old shape. So the new one is the one with all the apostrophes, x prime, y prime, z prime, 8/4. That tells me that 2 is my scale factor here. So when I do the dilation portion of this, I'm going to be dilating with a scale factor of 2. And sometimes doing the dilation first is a good idea. And sometimes doing the dilation first is going to take you off the page a little bit. Like in this case, if I did the dilation first and multiplied all my coordinates by 2, I'm going to end up like way over here somewhere for a lot of these coordinates. So for this particular one, doing the dilation first might make things more difficult. Also, something that you could notice is that the coordinate for z prime is on the origin. That's generally a nice point when it comes to dilation. So if I can move z over to z prime first, since it's on the origin, that might be a good first step here. So I'm going to decide to try translation first on this one. And for z, we're going to move it right 1, 2, 3, 4, 5, 6, 7, 8, 9. So step 1, translate right 9, and then up 1, 2, 3, 4, 5. So that's step 1. And then once I do that for all of my coordinates, let's see, x ends up there and y ends up here, moving it right 9, up 5. This is where my triangle lands prior to dilation. Now I'm going to try the dilation with scale factor of 2 about the origin. So what that tells me is I'm going to take all my coordinates for this little triangle and multiply them by 2. So instead of over 8 up 0, or sorry, over 4 up 0, it's going to be over 8 up 0. Instead of over 2 up 4, it's going to be over 4 up 8. And 0, 0 stays the same because 0 times 2 is 0. So now my triangle lands exactly where I want it to. And we're good to go. This would be considered a complete problem. We've shown with transformations how I can get from this triangle to this one. One more thing I might note on this one is that sometimes you'll start seeing your directions for dilation written like this. And this just means dilate with a scale factor of 2 about the origin. So our scale factor is going to be right here. And since it doesn't specify a different center of dilation, it's going to be centered at the origin. So this is going to be something we want to be able to recognize from here on out. Okay. So let's go ahead and turn the page and look at another one of these. We're going to do the same thing with this one. So we're going from JKI to J prime, K prime, I prime. And on this one, we don't have any horizontal or vertical sides that we can count to figure out the scale factor. There's a couple different routes you could go. You could use the distance formula and figure out the side lengths on some of the sides that are supposed to go together and do it that way. Or you could count, let's go with J and I. The horizontal distance from J to I is 4. The vertical distance, so if I go over 4 and then I go down 2, the vertical distance is not 4, 2. And then I might do the same thing on J prime and I prime. My horizontal distance here is 1, 2, 3, 4, 5, 6, 7, 8. My vertical distance is 4. So to get from J to I here and J prime to I prime here, the vertical or the horizontal distance, sorry, changes by multiplying it by 2. And the same thing happens with my vertical distance. So the vertical and horizontal distances change by multiplying them by 2. This can also tell me that my scale factor is 2. All right. So then, on this one, I would probably also start with translating because, again, if I start dilating this with a scale factor of 2, I'll end up a little bit off the grid, which is fine. So if you want to start by dilating, you can. But on this one, I would probably also take advantage of the fact that K prime is on the origin and translate K over to the origin first. So for this one, first step again is going to be translate. I'm going to go left 1 and then up 6. So I'm going to do that with all my coordinates. Left 1, up 6. Left 1, up 6. So this is where my triangle lands to start with. Once I've done that, then we can do the dilation part. And it's going to be with a scale factor of 2 again about the origin. So this coordinate, instead of 5, 2, becomes 10, 4. This one, instead of 1, 4, becomes 2, 8. And we've arrived at the larger triangle. All right. So those are one kind of problem that you might end up with. Another one is something more like this, where you have to graph both of the shapes, and then you have to decide, are they similar or not? So we'll look through one of those. For ABC, we have to go over 1 up 2, over 2 up 2, and over 1 up 4. A, B, C. And then for DEF, it's 4, negative 6, or 6, negative 6, and then 4, negative 2. All right, so the first thing I start thinking is, do they look similar? Because if they do, then I start trying to find ways to show that they're similar. If they don't look very similar, then you might want to start checking side ratios and stuff like that just to be sure. But in this case, I would start by looking at the sides that I can count the length of. This one is 4 units long, this one is 2 units long, and this one is 2, and this one is 1. So 4 over 2, since these vertical sides go together here, if that's the same as 2 over 1, then that's a pretty good indicator that we're in business and we should start trying to use similarity transformations to show that they're similar. And they are. 4 divided by 2 is 2. 2 divided by 1 is 2. Our scale factor here is probably 2. So we'll go ahead and check here using our similarity transformation. So I'm going to dilate and then move this thing around to show that it will indeed land on top of DEF. So on this one, I'd probably go ahead and dilate first. You could translate and then dilate, or you could try to do just dilation where you pick a different center of dilation that would make this land on top of DEF. But the easiest thing to do here is probably going to be to start with dilation. Dilate triangle ABC with a scale factor of 2 about the origin. You'll notice that the scale factor is often 2 or 3 or something like that, because anything bigger, you're going to end up, unless you rescale the graph, needing a lot more space. So making this dilated with a scale factor of 2, instead of over 1 up 2, it's over 2 up 4. Instead of 2, 2, it's 4, 4. And instead of 1, 4, it's 2, 8. All right. So now this looks like it would be the same size as DEF. And now all I have to do is translate it into position. Sometimes you'll end up having to reflect it or rotate it into position, but since these are oriented the same way, we can just translate to get it where we want it to go. So next step, translate. I'm going to have to move it right 2 and down 5, 6, 7, 8, 9, 10. And I would double check my points just to make sure. Right 2, down 10, right 2, down 10. Yep, it works out. It lands exactly on top of DEF if I do this. Okay, so those are the kind of main types of problems that you're going to see with this. The homework assignment, if you're in my class, is the next 2 pages here. You're going to see some problems where you have to do a composition where you rotate and then dilate. And then you'll see ones just like from our examples where you have to describe the transformation from here to here, or ones just like we did with the example we just had, where you dilate, or where you have to graph the thing and then figure out, what you're dilating by and if they're similar or not. Just so you know, on the second page where there's 2, or where there are 4 problems, 2 of them are going to be not similar. So 2 of them are similar, and 2 of the problems have shapes that are not similar. So that's your hint. Have fun, ask questions if you have questions, and have a good one.